Welcome to a lesson with Dr. Powell. Let's take a look at what it means to go backwards in the differentiation process. Suppose, for instance, we have a derivative like ds dt, this is a cursive s, is equal to t squared plus 3. Let's suppose that s represents position of movement on a straight vertical line up and down. So ds dt is going to be the rate of change of position with respect to time, which is speed, or since we have an upward and a downward direction, speed with direction is called velocity. So it could be negative or positive for the derivative. So the question is, what is the position function originally? Let's take a look at how we would go backwards in this process. So we're given a derivative and we want to find the function that has this as its derivative. Well, think about the power rule. Let's think about how the power rule works backwards by first thinking about how it works forwards. This is how it works forwards. Like suppose, for instance, we have something like t to the fourth. This is not related to the initial question. This is just a side note, kind of for an example, and then we'll apply the side note to the specific. So here, let's suppose you have something uncorrelated with what I gave you originally, just t to the fourth. And let's see, what do we do first? The first step is to multiply by the beginning exponent of 4. So multiply it, put it out front. And so that's like multiplying the whole expression by it. The next step is to subtract 1 in the exponent position. So the exponent in the exponent position, we have 4, so we subtract 1 from it to get 3. This would be the final result. Now let's suppose that we start now with 4t cubed and try to work backwards. And we want to reverse these steps. So notice I reversed them, and the way I did it is I reversed the order and I reversed what was happening in each step. So instead of subtract 1 in the exponent position, first we start by adding 1 in the exponent position. So starting with 4t cubed, we then have 4t to the fourth. Then the next step is to divide by the ending exponent. The ending exponent is 4, so we divide by it. So 4t to the fourth divided by 4 is equal to t to the fourth, which is what we wanted. So kind of in summary, what we have is given something like t to the 6, so I'll give you a different example here, t to the 6, and we want to take we want to go backward, take a backwards derivative, say. It's usually called an antiderivative because you're not taking a derivative, but you're going backwards. So we usually use say anti means against or backwards. So the antiderivative of this, the first thing to do is add 1 to the exponent. The next thing to do is to divide by that new exponent. So the nice thing about taking an antiderivative is you see right here and here the same thing. So we can change our variable. What if we have like x to the 15th? What's the antiderivative? X to the 16th divided by 16. You see the same thing here and here. It's just 1 more than what's here. It's kind of nice how you see the same thing in both locations. So it's a pretty simple, straightforward rule. Now, what happens if you have something multiplied to the front? Like suppose you have like a 5 times x to the 15th. What would that do? Well, just like when you take a derivative, this constant stays multiplied or on right here. It stays multiplied on when you work backwards as well. Backwards and forwards, it'll stay there. So we just have 5 times x to the 16th over 16. Okay, so I think we're ready to tackle the initial question, at least make some headway on it. Given ds dt is equal to t squared plus 3, let's try to find out what the original function is, s of t. So take a look at t squared. We can think of it as t cubed over 3 when we take an antiderivative. Notice we're going to do this since derivatives split across addition, so do antiderivatives. Working backwards also splits across addition. Now, anything that derivatives don't split over, antiderivatives won't as well. In fact, it becomes more complicated how to work backwards in those cases. So, but for addition, it still stands. We can still do this. So for this one, 3, let's think about what we could have here such that that would be its derivative. Simply 3t. You could think of the backwards power rule with a t to the 0 if we wanted to. going to 2 the first over 1. But really, we can also just think, well, if you have a slope of 3, that comes from a straight line 3t. So we get this. Now, is this the result? Well, we have to be careful because in the derivative, you also have a plus 0. And what has a derivative of 0? Well, any constant at all. So really, we have some variability in our result. We don't our result right here for our position. We have infinitely many solutions because we have infinitely many things we could put in for a particular constant here. This right here is called the general antiderivative of this function here. Take this function, its general antiderivative is given right here. Sometimes we have a notation for finding a general antiderivative, just like we have notation for derivatives. It looks something like this. It's kind of odd and funny, but this is called the indefinite. See why it's indefinite? That means that comes from this plus c here. So what we did is we found a particular antiderivative, and then we just added on a c, and that becomes the indefinite integral, is what we call it. So when we're taking a derivative, it's like we're analyzing something and looking for a rate of change. Now, when we go backwards, it's like we're unanalyzing it or reintegrating it. Integrate means come together or unify, putting it back to where it came from. So now this notation, let's explain it. This is like a big S, because when we're integrating or putting things back in together in a whole, it's kind of like we're having a big sum, or we're summing things up. This dt multiplied on kind of reminds us of the following idea. This is just notational. This really doesn't mean anything. This is just notational. Let's suppose you take a derivative and you put this symbol on and you put this symbol on. Now what happens? These symbols cancel. Then you're left with adding up lots of little ds's. And what happens when you add up a lot of ds's? You just simply get s. It's notational. We'll talk about more meanings of this later, but for now, we're just going to take it as a notation, just like we take a notation for taking a derivative, such as d over, for instance. We commonly use this notation, d over dx, when we're taking a derivative, or this when we're taking a derivative as an operator. Similarly, we're going to have an operator that looks like this. Take an antiderivative of that, and we get this. This is the general antiderivative. Keep in mind, we don't particularly know which constant to put in until we have additional information. For instance, let's suppose we had the information that at time t equals, maybe this is seconds, 1 second, we knew that the position was simply 0, or right in the middle. So what does that mean? That actually can tell us what c should be, because we can throw in this 1 here for t, and in evaluating it, we get a third plus 3 plus c is equal to 0. Then we could easily solve for c, and we would get, and we would end up getting -10/9 for c if we were to evaluate that. Let's see, is that correct? Yes. Okay, we'd end up getting this. And so in that case, we could just throw this in, and then we'd actually know exactly what it is, and we'd get a specific antiderivative. A general antiderivative is called an indefinite integral, and a specific antiderivative is just called specific antiderivative. So the specific antiderivative in our case, if we made the condition that s of 1 is 0, so we have enough information to find out a c. So just knowing the derivative is not enough to figure out what the antiderivative specifically would be. You'd have to have some other information to be able to solve for what a constant is, such as this. Then in that particular case, we'd say that the specific antiderivative would be s of t is equal to t cubed over 3 plus 3t minus 10/9. Thanks for watching.